Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. 3D printing of ceramics is a hot topic right now. Also known as additive manufacturing, 3D printing allows for increasingly smaller or complex structures to be created as techniques improve. New research into the 3D printing of silica glass could pave the way for future advances in the printing of ceramics. Methods for 3D printing of such structures involve high temperatures, produced by using either a laser or a furnace to obtain temperatures of around 1000 degrees Celsius, often at high pressure. The latest research has shown that such high temperatures are not required. Printing of silica glass is possible at around just 200 degrees Celsius if you introduce photochemistry.
We're using this kind of chemistry that actually exists for a while. People know that things probably back to maybe 1990 or early 2000. It's an interesting approach. It's basically you can convert polymer, a special polymer, elastomer, into ceramic. People have done a little bit of work on that, but not really on the 3D printing. So we kind of utilize that approach, combine that with 3D printing, we can generate parts with complicated shapes.
That was Professor Jerry Chi from the Georgia Institute of Technology. After using 2-photon polymerization to cross-link polydimethylsiloxane, his team then used deep UV to convert the polymer into silica glass. The deep UV irradiation is carried out in an oxygen-rich atmosphere. The UV light converts the oxygen to ozone, which then goes on to react with the polymer, prompting the formation of silica glass. Structures of several tens of micrometers in size can be fabricated with a resolution of a few hundred nanometers. Using deep UV light, the process of converting the polymer to glass and removing the excess carbon takes around 5 hours, much shorter than the 20 to 50 hours required for traditional techniques.
The property change is also dramatic because when we print the sample, the stiffness of the sample is like your skin, very, very soft. The modulus is about 100 kilopascal. But when we shine the light for about 3 or 4 hours, and the modulus becomes like bone. So the modulus goes about 30 gigapascal. So you can see the modulus change almost 5 orders magnitude. So it's a really dramatic change, yet we can also maintain the shape. So it's kind of an amazing process.
Several structures were printed, including lattices, the Georgia Tech Buzz mascot, and a smooth miniature lens with a diameter of 150 micrometers. The role that the ozone plays is intriguing. Dr. Minjo Lee, who is a postdoc at Georgia Institute of Technology, explains that several factors have to be taken into account when using the deep UV or DOE photochemical reaction.
We want to fully convert these 3D structures. We need to facilitate this process. So we want to find out the optimal condition for this DOE conversion process. And we have done a lot of parameter study, the flow rate of the oxygen, and also the environment, the experimental setup, like the distance between the DOE light and also the sample, so that we find out this optimal condition for this conversion. If without a proper design, structure design, basically you will after the DOE conversion, you will generate some like cracked samples because of the shrinkage. So we have to carefully design this structure on the that to be printed on the substrate.
The micro lens could have uses in optical devices, and the team also produced a structure with a hollow microfluidic channel with a diameter of 30 micrometers. Such tiny silica-based structures have applications in medical devices, optoelectronics, semiconductors, and more. To realize the full potential of this new fabrication technique, the team will continue to refine it and determine the exact role that the ozone plays. The structures they have made so far have a density below that of conventionally made glass components and a low modulus, properties that are not favourable for applications that involve load carrying. The current achievements represent a significant learning curve that the team will build on.
It took us about 2 years almost. One big challenge is how you can actually return the structure without damage on the structure So initially when we started, we print the thin film, we just shine the lights, and then you see promising results, but you see lots of small pieces of glasses on the floor. And then we gradually learn more. Then we know you need the substrate to support, and then you can return the structure.
All the experiments are quite challenging because the samples are so small. I think the most exciting part is the low temperature we achieve, which is like only 200 degrees Celsius, which is far below the conventional method, usually about 1000 degrees C.
The low temperature is particularly beneficial for in situ printing of microelectronics, where semiconductors cannot withstand the higher temperature of conventional methods. The team is working on printing larger structures and will use light with a higher intensity than the one they're currently using as a first step to refine their new fabrication process. This work was published in a recent issue of Science Advances. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at mrsbulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.